Well, good morning. I'm moving now towards Europe and to a very small country. It's certainly a complex topography. It's not really a city, but some people say it's slowly growing into a city because we have a very large population growth in Switzerland. So I will talk about estimation of country-scale methane emissions using observations and inverse modeling, another inverse modeling talk. I will actually only refer to ground-based observations because I realized there's too much material to show both of them, and we are less confident also with the results from our airborne observations. So I will actually focus on ground-based. I would like to thank my co-authors, which have done the measurements, like Brian Oney sitting here, and especially Stefan Henne, who has contributed a lot to the modeling. Now, if we look at methane on a global scale, and this is a pie of the contributions from different sources. We have in these bluish colors different natural sources, and we have agricultural sources from ruminants, rice agriculture, and then we have other sources like gas and oil industry, coal mining, landfills, and waste are important sources. So that's the global pie. If we look at Switzerland, the situation is very different and much more boring actually, because we have a very dominating contribution from agriculture, from ruminants. More than 80% we think are from agriculture, as we summarized in this publication earlier this year. So the total emissions are about 180 gigagrams, which is less than 2,000th of the global emissions, so it's not a very large contribution Switzerland does. But anyway, our ministry was interested in quantifying or assessing our inventory because we report annually to the Kyoto Protocol, and we would like to know whether this is correct. And the total uncertainty estimated for Swiss emissions is of the order of 16% based on the bottom-up estimates. Natural emissions, as you can see, make up only a very small fractions according to our assessment. If we do inverse modeling, we of course need not only the total, but also the distribution of the sources. So we've developed this spatially explicit inventory on a 500 meters resolution for the whole of Switzerland. You can see this here is the total of all sources. This is just a contribution from agriculture. You see here in the Swiss plateau, on the southern side, there's a lot of cattle farming. So that's the area of the highest emissions. And then if you look at the energy sector, that's basically gas distribution contributing that we've focused on Zurich and cities like Basel or Geneva, where we have the highest emissions from this sector. In this study I will focus on Swiss Plateau, which is squeezed in between the Alps and the Jura mountain, so relatively flat, comparatively flat terrain where most of the population lives, and as you can see also most of the cows are living. So we can also compare this to EDGAR and TNO-MAC inventories, other emission inventories at much coarser resolution, as we have just seen before for the Bay Area. We can see that actually EDGAR estimates 30% more emissions for Switzerland than we have in our bottom-up estimates, the national inventory. And you see it's also the distribution is shifted towards the north, more towards the populated areas, away from the agricultural areas, so it's a shift in the distribution, whereas the TNO-MAC inventory agrees both in the total number and in the distribution much more with our high-resolution inventory. These are just the relative difference maps to our inventory. Now the questions that we ask ourselves, can we actually validate our emission inventory based on atmospheric observations on a small scale, such as Switzerland, in a complex terrain? And can we maybe resolve some of the differences between the inventories, whether we see some is more realistic than the other? But also, do we maybe find methane sources that we don't account for yet? So we've set up a measurement network within Switzerland in the framework of a project called CarboCount-CH, which is actually mainly targeted at CO2, but in this study we focus on methane. So we've set up 4 new sites, all equipped with Picaro instruments. One is a tall tower site, 217 meter tall. Gimitz is a 30-meter tower in a completely flat area of Switzerland. Lagon is also a 30-meter tower, but on a mountaintop. And Frübühl is on a plain, but also on a mountain, in a mountain region. And Yeah, and actually we also used some of the Jungfraujoch measurements to determine the baseline concentrations for one of the inversions. So for the modeling, we use FlexPart, and we have developed our own version of FlexPart coupled to a Cosmo model, which is a numerical weather forecast model operated by Météo Suisse and other weather services in Europe, similar to WRF, I would say. So we can run FlexPart here at the resolution of 2 kilometers in an inner domain, and then at coarser resolution further away once the particles leave this domain. So nested configuration. And we release every 3 hours 50,000 particles from each site, follow them backward in time over 4 days. In addition to check for sensitivity to the meteorology, we also tested with the standard kind of FlexPart ECMWF, where we have coarser resolution 0.2 degrees input data for the domain. So I think I don't need to say much how we get from air particles that we follow to concentrations. So FlexPart gives us these source sensitivity maps. If we multiply this with our inventory, sum up the map, then we get an atmospheric enhancement. And so we do that every 3 hours. So we get the time series, which we can compare with the observations and put into an inversion framework. And actually, we've used 2 inversions. My colleague Stefan Henne is running kind of a standard Bayesian inversion, and I'm using an extended Kalman filter inversion, which I presented 2 years ago in a publication. A main difference is that this is kind of putting all the measurements into the data, into the inversion at once, whereas I do a sequential assimilation and day by day, and the measurements slowly adapt the emissions to better match the observations. And important in both inversions, we also make an estimate of the baseline. So the background concentration, which is not covered by this transport simulation, is important, and we also optimize for that. So common settings, we both use the same a priori emissions, and the total a priori uncertainty in our inversion we scale such that we match the 16% uncertainty for the total of Switzerland. And we use only afternoon observations because we have more problems with nighttime measurements. And I should maybe also say that our inversion, we have an irregular grid, so we have much higher resolution grid near the sites, and of course a resolution further away to reduce the inversion problem. Here's just a figure showing well, the performance of our inversion of simulations. Here is for the tall tower site Beromünster, measurements at 270 meters actually, not 212. And black is the measurements, blue is the a priori estimate, and red is after optimization of the emissions, where we have a better match with. But you can see that we are very nicely able to follow the variations in the measurements with the model. What you also see is this green line, which is the baseline that I estimate in. Together with the emissions, I get an estimate of the baseline concentration, that you can see that it's slowly varying with time. That's how I set it up. Take another site, Legon on a mountaintop, a very similar picture. Actually here the top is at a similar altitude as Beromünster, and we have both sites share basically the synoptic variability. But one problem with Legon is that if you look at the model topography is much lower, then it doesn't resolve the steep topography at this site. So for the model, it's more like a tall tower site as well. But of course, you have local flows that are not nicely resolved, so that's the basic problem of mountainside. And we see Legon also in winter has much higher concentrations than Beromünster, so more local sources influencing this site. And finally, Gimitz in a totally flat area. We see similar picture here. But actually, especially here in winter, we have very high concentrations, and the most striking is that we strongly underestimate in our a priori the concentrations that we measure at Gimitz. So obviously there are some sources around this site that we don't cover in our inventory. Well, this is just a figure of the distribution on our reduced grid. This is again the prior emissions based on the combined Majoliga-Thionot-Mecque inventory, Majoliga inside and Thionot-Mecque outside of Switzerland. And this is the posterior estimate, so we attribute much more emissions to southern Germany, so it's always nice to blame the others. But we also see reductions in this area and increases in eastern Switzerland. And this is the error reduction. I will not say more. This is another way of showing this result. I don't know why this ruminance shows up here, that this shouldn't be there. What is shown here is the relative change compared to the prior. So our posterior estimates the less emissions in these bluish areas and higher emissions in the orange areas. So towards the east or southeast, we see less emissions in the posterior than in the prior, whereas we estimate higher emissions towards the eastern sector. And we can actually compare this also when we use a different prior, the EDGAR inventory. And here because we start at a higher level with EDGAR, 30% higher, we have more bluish, so we reduce more in this area. And the most striking is these two areas where with EDGAR, when we put in EDGAR as a prior, then we have to strongly reduce the emissions in these areas. That's Zurich and Basel. So EDGAR attributes much too high methane emissions to these urban areas. I also made a sensitivity when I add another site. So this was an inversion only, the base inversion is only using these two sites where we have the most representative measurements. Here in this, if I add Gimitz, you see that there's quite a substantial change. I see some increases already here in using only these two sites, but when I add Gimitz, then this area receives much higher emissions, whereas this area here is still negative. And this is actually one of the areas with the highest cattle density within Switzerland. Whereas this area has in the a priori really low emissions, and we currently don't know where these emissions are coming from. So I also compared with another Bayesian inversion from my colleague. You see that the pattern is quite different. We agree on this negative data here, but towards the northeast we see quite some differences. We are currently investigating the reasons, but I'm very sure that it has to do with the different treatment of the baseline in our approaches. Maybe I can say more in the conclusions. Well, if I sum up all these results, I get this figure here. So this is, each bar is showing the total methane emissions in Switzerland. Blue are the prior, and this is our Maiolica prior, and this is the EDGAR prior here. And then the red is the posterior from the extended Kalman filter inversion and the posterior from the Bayesian inversion in green. And you see that in this baseline case with Lagon and Beromünster as measurement points, we agree quite well. If we put in EDGAR, I find a relatively clear reduction compared to EDGAR, getting closer to this estimate. And with the Bayesian inversion, we also see a reduction, but a little bit smaller. The largest effect, as I already mentioned, when we put in Gimitz, an additional site, I have a quite substantial increase, so we end up about 30% higher than the prior with adding this site. And if I double the uncertainty of the prior, I don't see a big change. This is very consistent with the baseline case. And putting in a different transport model, ECMWF, instead of our Cosmos simulations, doesn't change much. So that's only a simulation done by my colleague. So this is basically the range we have from all these different sensitivity runs, and that's at the moment kind of the area where we think is probably the most realistic estimate for the emissions. And you see it's higher than our prior, but it's somewhere in the range of the EDGAR emission, although we see a very different distribution than in EDGAR. So to sum up, I've used an extended Kalman filter and Bayesian approach to estimate emissions. We see decreases towards the west and increases towards the east, which most likely is not a very realistic case, but has to do with the problem that the way we treat the baseline, we assume that we have the same background concentration when the air is coming from the Atlantic than when it's coming from Eastern Europe, and that's not a very good assumption. So actually, most likely the baseline, the background concentration should be higher when we have a direction from the east. And so this problem has to be compensated by the emission estimate. And that's something we really need to work on. Interesting is that we don't think that the high emissions gas leaks estimated by EDGAR over the cities is realistic. But we see reductions in the cattle area, but around Gimitz, we currently don't know what the source is. We generally have an increase by 16% over Switzerland. And yeah, I think that I'll leave it with that. Thank you.
Thank you. We have time for one quick question. Yes.
I came in late, sorry for that, but why are gas leaks highly unlikely? Why do you say that?
Because when we, the Edgar inventory puts a lot more methane to the urban centers than we have in our best estimate Swiss inventory. And then when we put that in the inversion, we see a strong reduction over Zurich and Basel.
Since we're ahead, we have time for actually one more question.
Steve?
I wondered, inversion method without that unit set.
Yes.
In the regions where the emissions changed a lot, was that change larger than uncertainties that you thought were associated with those cells originally?
Well, the grid-based uncertainties are relatively large. They are 16% for the total of Switzerland, but I think the individual grid cells have uncertainties more of the order of 40%. So I'm not sure that's outside it.